right, well, we're very lucky to have Peter Shor to start the session today with a talk on scrambling times and black holes.
All right, thank you. So, most of what I'm going to talk about is not new, and it mostly appears in two papers I wrote 3 and 4 years ago, but I don't think this is that widely known, and I really like the results from the questions, so I'm going to talk about it. So, I'm talking about scrambling times and black holes, and I think first I'm going to give you a little bit of black holes and information so that this gets put into context, and then I'll try to explain the difference between weak scrambling time and strong scrambling time. These probably aren't the best names for them. Maybe they should be named OTOC scrambling time and entanglement scrambling time. And finally, I want an argument that fast, strong scrambling for black holes implies non-standard physics. That there has to be something really weird about physics for black holes to be fast scramblers in the strongest sense of fast scramblers, and then end with some speculations. So black holes are a consequence of Einstein's theory of relativity, and a Schwarzschild, that's spelled wrong somehow. Black hole is one that has no charge or spin, and these are by far the most easy kind of black holes to think about and to do calculations on. So that's what I've done. Really, someone should do the same thing for Kerr black holes. And black holes. So we're going to be using natural units where all physical constants are 1. The surface area and black holes have certain things you can prove. The surface area of the horizon always increases, and this was proved by Christodoulou. It's reminiscent of entropy. Entropy always increases. And second, Bekenstein actually, found found that black holes really behave like they had entropy. So entropy is the area of the surface area of the event horizon over 4, which is 4 pi m squared, where A is the area of the horizon, m is the mass, and black holes radiate. So a Schwarzschild black hole emits black body radiation at a temperature of 1 over 8 pi m, where m is the mass. So this is an incredibly small number for any realistic black hole, which means we will never see Schwarzschild radiation in any time in the foreseeable future, but there are enough theoretical reasons for believing that there really is radiation.
Unless there's a microscopic black hole.
If there's a microscopic black hole, it will radiate strongly enough that you don't want to be close to it. And it will end with a burst of energy, which I think is not too different from an atomic bomb, which you'd think it would be much larger, but it's not. It's not terribly, a destructive explosion, but not an incredibly destructive explosion. So, black hole information paradox. Well, general relativity says that any information thrown into a black hole can never come out. That's because, at the event horizon, if you have something going at the speed of light coming out of the black hole, it will just stay at the event horizon because, because space is curved, so that so general relativity is pulling it inwards and it can't escape. And you can think of this as it's being attracted towards the singularity of the black hole by the force of gravity, although, you know, if you believe in general relativity, gravity doesn't really exist. It's just curved space. But, and so if the black hole evaporates, the information must be destroyed. And to support this, if you look at Hawking's derivation of Hawking radiation, the radiation that comes out is completely uncorrelated with the stuff that fell into the black hole. But of course, you can argue that this derivation uses semi-classical gravity and is only an approximation. So maybe if we knew the real theory of physics, we would understand how information comes out of a black hole. But quantum mechanics says that physics is reversible, so information can never be destroyed. And this wasn't a problem before it was discovered that black holes evaporated. And there was a bet between Kip Thorne, Stephen Hawking, and John Preskill that the information about whether the information is destroyed or it escapes. And Hawking conceded, but Kip Thorne and John Preskill still have not settled their bets. So I think this shows that physics is still unclear about whether the information escapes or not. So Hawking, okay, so if you have someone hovering in the black hole, so they're accelerating outward at a rate so that they will stay at the same point relative to a stationary observer, they will see, well, maybe you should call it unruh radiation. So Hawking radiation and unruh radiation are very closely related. An accelerating observer sees unruh radiation, and this is basically thermal radiation at a certain temperature. And for someone hovering just above the event horizon, this is essentially equivalent to the Hawking radiation. And the radiation seen at height h in Schwarzschild coordinates is given by the temperature equals 1 over 4 pi square root of 2 mh, where h is here is not Planck's constant, but the height above the event horizon. So, okay. So Susskind worried about this, and he came up with an answer he thought answered the question. So what Susskind reasoned is if someone jumps into a black hole holding a quantum bit, for an outside observer, this qubit must emerge somehow because information is never destroyed. But if you jump in holding a qubit, you reach the singularity at the center of the black hole. Of course, we don't really know that this singularity exists, but and you see the qubit annihilated at that point. So the question is the information destroyed? And he asked, can you reconcile the point of view of the observer falling into a black hole and an observer staying outside the black hole? And his complementary principle is the idea that because these observers can never get together and compare notes, it doesn't matter if they observe contradictory things, because, the universe is never going to admit that it's behaving contradictory, because the two observers seeing contradictory things can never get together and compare notes. So, I mean, is this a reasonable interpretation of physics? Can the universe be inconsistent if this inconsistency is never revealed to anyone? Okay, so this is a philosophical question, and maybe this is a little stronger than Suskind's complementary principle. But in 2012, 4 people with the initials AMPS really destroyed Suskind's theory of complementarity. So complementarity contradicts some fundamental theorems of quantum information theory. And what they said, well, if the information comes out, then the information inside the black hole must be entangled with the information outside the black hole. On the other hand, if you just believe in physics and you believe that an observer falling into the black hole doesn't see anything unusual when he crosses the event horizon, then there must be a massive amount of entanglement between the stuff right inside the event horizon and the stuff right outside the event horizon. Actually, I should say the vacuum right inside the event horizon, the vacuum right outside the event horizon. But that means that the stuff inside the black hole is entangled with two different things. And we know from monogamy of entanglement that something can only be entangled strongly with one other object. So complementary doesn't work. And one question is, how much of complementarity can we save? And does the outside observer's point of view make any sense if we completely ignore the point of view of someone falling into the black hole? So Hayden and Preskel thought about these things, and they realized that with quantum information theory, if you have a system that is maximally entangled with a black hole, and what this is you make a black hole, and then you collect all the information all the Hawking radiation that has come out of it since it was created, which is an enormous amount of Hawking radiation, but there's nothing wrong with collecting it. And then you throw something into the black hole, you can get the information on what was thrown in just from a few bits of the Hawking radiation and this enormous amount of information that you've collected. And this is not true, not just for a black hole, but for any quantum system that's maximally entangled with another system. And we believe that black holes are quantum systems, so this should apply to black holes. So here's Hayden's and Preskel's argument in more detail. You collect the information that has escaped from the black hole until the black hole is half the size it started out, which means you've got half the radiation. And this point, or half the information. At this point, the interior of the black hole must be maximally entangled with the radiation that's escaped. Now you throw a qubit in the black hole and you wait for the scrambling time and collect order log n bits of additional Hawking information. And from this, you can then do a measurement that gives you information about what was thrown in. And because the Hawking radiation you collected is maximally entangled with the black hole, you can use it to make any measurement you could have made on the original qubit that you threw in. So Bob throws in a qubit. He waits for log m time, which is not very long for realistic black holes. And then he jumps in, hoping to catch up with the information he has thrown in. And if he catches up with the information, the qubit he has thrown in, he now has two copies of the qubit, which is a violation of the quantum no cloning theorem. So we know that for physics to be consistent, he can't catch up. And how long can he wait before it's impossible for him to catch up? Well, it turns out that he can wait m log m time, and by, putting a relativistic jetpack on and diving into the black hole as fast as is I shouldn't say humanly possible because it's not humanly possible, but as fast as is physically possible, he can catch up if he jumps in less than m log m time. So in order for the no cloning theorem not to be violated, the scrambling time must be at least order m log m.
Can you define the scrambling time?
That is the whole point of the talk. So what is scrambling time? Well, no, I mean at least order n log m, because he has to wait for at least the scrambling time before he jumps in, and if he can jump in before order of amalgam, he can catch up with the qubit that he threw in, which would be a contradiction of quantum mechanics, which we don't believe that black holes contradict quantum mechanics. So what is scrambling time? There are several definitions that have been used. One is the time it takes for the out-of-time order correlator, OTOC, to equilibrate. And I will define this more later. And two, the time it takes for the system starting in a arbitrary product state. So divide your black hole into two pieces, say the northern hemisphere and the southern hemisphere, and start with the northern hemisphere unentangled with the southern hemisphere. Actually, that's not possible because of quantum vacuuming. They will always be entangled, but they could have a minimum amount of entanglement, which is just the order of the boundary between these hemispheres, or they could have a maximal amount of entanglement, which is the order of the volumes of these hemispheres, or actually I should say surface area, because, yeah. So the time it takes for the system starting in a near product state to become nearly maximally entangled, and time 2 is at least as large as time 1. So this is easy to see. So Sakino and Susskind use a third definition, which I'm not going to go into. And a fourth definition is based on the tripartite mutual information, and there are probably more definitions that have been proposed. And so what we're going to argue is that for real black holes, time 2, this is what I've been calling the strong scrambling time, although I probably should call it the entanglement scrambling time, must be large, even though time 1, the OTOC scrambling time, might be small. Okay. So Yoshida and Kitaev show that the definition 1 is what's required for the Hayden-Pascal protocol. So as long as the out-of-time order correlator is equilibrated, then you can deduce the qubit that you threw in from the state of the black hole, which is maximally entangled with information that you have, and the small amount of Hawking radiation that you collect. And with Aram Haro, Lingang Kong, Ziwen Liu, and Said Meiraben, I have a toy model where we can prove that these two scrambling times can be different. In fact, the time 2 can be exponentially larger than the time 1.
Sure, I'm confused. If the scrambling time is fast, that seems like it would sharpen the paradox rather than diffuse the paradox. I mean,
if the scrambling time is fast, that's right.
It does. Okay,
Yeah.
it does. I see, and so you're saying, so if one is if the scrambling time 1 is small, and if that is sufficient for the paradox, then the point is that we do have the paradox in full force.
Well, it's not but scrambling time 1, we can assume it's long enough for that Bob will not be able to jump in and catch up with the qubit.
Okay, I see.
But the thing I'm claiming is that time 2 might be exponentially larger than the small time 1.
Okay.
Okay. So what is an out-of-time order correlator? Well, we have two operators, W1 and W2. W1 operates at time 0 in position X, and W2 operates at time T, which is later than time 0, and position Y, which is far from position X. And we look at the commutator, W1 of 0x and W2 of Ty. And this commutator basically gives some indication of how long it takes the effects of W1 to reach the location of W2. I'm sorry, I switched variables and I did not, forgot to switch them in this paragraph. So the out-of-time order correlator is the trace of W of T, V of 0, dagger, W of T, V of 0. I haven't told you.
Okay.
we have a Hamiltonian. And you can think of the out-of-time order correlator as first you apply W1 of 0x, and then you apply unitary evolution going forward, apply W2 of ty, apply this unitary, undo this unitary evolution and go backwards in time, and now you apply W1 of 0x. Again, go forward, and W1 0 of x inverse, go forward, W2 of ty, and go backwards. And if the information from this operator has not reached this point yet, this whole evolution is the identity, which means that the commutator is 0. On the other hand, if this point has, if the information from here has reached here, it's not the identity, and it's positive because, well, basically because the way we wrote it down, this is a square, so it has to be positive. So there's a very simple lower bound on scrambling time. The system with radius r needs r over c, here c is the speed of light, time for information to pass from one side to the other. And that means that the scrambling time has to be at least order of m, since the radius is twice m is the mass, and c is 1 in our calculations. So what Hayden and Preskill did was they showed a lower bound of order m log m, assuming the no cloning theorem holds for the scrambling time of black holes. So now I want to give you the toy example, which shows you that these two scrambling times can differ radically. So we're going to put the qubits on the vertices of a binary tree, and the time evolution runs by we choose a random edge, and then we apply a random 2-qubit Clifford group element to that edge. So we choose edges according to a Poisson process with rate 1. So for each unit time, there's approximately 1 Clifford group element applied to any edge. So this, I mean, it doesn't really matter how we choose. I mean, it doesn't really matter what rate we choose them, as long as we choose the edges to apply the Clifford group element in a random order, but this is a very convenient way to do it. So, and now let's let the operators W1, 0x and W2 of ty be Pauli operators. Let's say x is this vertex and y is this vertex. And when we apply a Clifford operator, what it does is it it takes the commutator of the Pauli operators, so it gives you another Pauli operator, and it takes identity, tensor identity to identity, tensor identity. So these are Pauli operators. And it takes any other sigma A, tensor sigma B to all possible non-identity sigma A's, tensor sigma B's with equal probability. So if you applied a Clifford operator to this edge, well, n tensor I, if you apply a Clifford operator to n tensor I, that's this edge, and here stands for any of sigma x, sigma y, sigma z, then n tensor I has probability 1/5. So this remains an I with probability 1/5. I tensor n has probability 1/5. So the n moves here and leaves an I here. And n tensor n has probability 3/5. So that means with probability 4/5, we get an n at this point. And in our toy example, let's take the binary tree. Let's put an n for every operator, for every non-identity Pauli operator, and I for identity operator, and just let this dynamic system run. I want to claim that we reach this point in linear time. Why is that? Well, let's consider the n closest to the point y. And let's let d be the distance from this n to y. So assume this n is unique. Then d goes up with probability 1/5 because, d goes up with probability 1/5 because we take whatever this is, tensor n to n tensor I, and then that moves the n backwards. It goes down with probability 4/5 if the Clifford edge, if the Clifford operator is applied to the edge after I, because this is, because with our little table, we get an n in this position with probability 4/5. So putting everything together, there's an equal chance of a Clifford operator being applied to this edge, and maybe the third edge out of n. So that means that this distance goes down with probability 2/10 and goes up with probability 4/10. Actually, I take that back. It's 2/15 and goes up with probability 4/15. And that's a random walk, which eventually reaches here in linear time. So that means that the time order correlator equilibrates in probability and time linear in the radius of this tree. Okay, now how about entanglement? Well, to get entanglement between the left side and the right side, you must have 2 to the n pieces of information on the left side, which match 2 to the n pieces of information on the right side, and then you can have linear entanglement because that's log of the Schmidt coefficient, essentially, log of the Schmidt rank. And this can only happen if a qubit moves from the left to right order of 2 to the n times, and that takes time 2 to the n because we apply a Clifford operator to this edge, on average 1 Clifford operator per unit time. So the entanglement scrambling time for this thing is 2 to the n. So this is really a huge difference between entanglement scrambling time and linear scrambling. And if you look at the physics literature, it's not clear that physicists have really been distinguishing between these two scrambling times. And what I want to do in the rest of the talk is try to convince you that these two scrambling times are really different for black holes, assuming that physics is not truly weird. Of course, we know that physics is truly weird, but assuming that physics is not truly weird in some completely unnecessary way. Yeah?
So in some literature, people also talk about entanglement velocity. So is your entanglement scrambling time related to what they call entanglement velocity?
What is entanglement velocity?
As an example, if you have a 1D chain, the entanglement grows linearly, we believe, of the half chain cut.
Yep.
And the slope is entanglement velocity.
Oh, okay. So yeah, so the entanglement scrambling time would be entanglement velocity, and they're really the same for spin chains for one-dimensional systems. Or rather, yeah, I want to say for one-dimensional systems, these two scrambling times are probably equal.
I see. But in the context of 1D, people call it butterfly velocity and entanglement velocity.
Yep.
And they show that their ratio can be arbitrarily tuned.
Oh, okay. So thank you. Yeah.
Yeah, sorry. Can you say a little bit about the toy model and why it's a good model for what you're
For?
It seems like you have a bottleneck at the top of the tree. So why is that? What does that represent in this particular context?
In the black hole context? Let me get to it. Okay. And I want one more comment. Since the density matrix obtained by applying a random Clifford operator is equivalent to the one by applying an arbitrary unitary with the, that means that our lower bound also works for arbitrary unitaries. So lower bound on scrambling time, and this is just a repeat of what I said earlier, it has to be m log m. So the fast scrambling conjecture, which Sakino and Susskind made shortly after Hayden and Preskel's paper, is that black holes scramble in order m log m time and are the fastest scramblers in existence. And some evidence for this is you drop some mass or charge into a black hole, it takes order m log m for the surface to equalize. And I want to claim that this is not a good argument, because suppose you put a drop of dye into a pitcher of water. The water level will equalize in a matter of seconds, and it takes much longer for the dye to diffuse evenly through the water. And this is because the change in water level is driven by an energy difference, while the diffusion of the dye is not. And similarly, distributing mass or electric charge uniformly around a black hole is driven by an energy difference, while distributing information is not. So there's no real reason why the information should diffuse as fast as the water level or the horizon equilibrates. And they had another argument that's out-of-time order correlation for functions in CFT, decay in time order m log m. And Schenker and Stanford argued that this should be fast decay in correlation functions because the CFT, there's a duality in string theory that CFTs are dual to anti-de Sitter spaces, and in anti-de Sitter gravity, scrambling time must be fast. But this is just for the OTOC scrambling time. And so what are our assumptions that we'll use to try to argue about black holes? We'll argue that from an outside observer's point of view, there's a consistent explanation of physics that makes sense, where you assume that nothing falls past the horizon in finite time. And actually, if you believe general relativity, nothing actually falls past the horizon from the viewpoint of the outside observer in finite time. So the interior of the black hole, well, it depends on how the black hole was formed, but the interior of the black hole could be relatively empty. So we're also going to assume that low energy physics looks more or less like the physics that we know, and that the causality structure of space-time behaves like general relativity says it does. And now what we're going to do is look at the space around a black hole. There's a region called the photon sphere, which is 1.5 times the event horizon radius, and there are no orbits inside the photon sphere. If you have a photon inside this photon sphere, either it escapes to infinity or it falls into the black hole. So the photon sphere is the radius of the smallest circular orbit for anything orbiting a black hole. And I want to make a side comment that this orbit is unstable, which means if you're just a tiny bit off this orbit, you will either spiral outwards forever or you will fall into the black hole. And there's something called the stretched horizon, and this is where the Hawking radiation is very high temperature. And it's really, I think it's a few Planck lengths in thickness. So outside the stretched horizon, physics should behave the way that we expect it to. And now we'll ask what carries the information to scramble it. And if the causality structure of general relativity holds, information cannot be transmitted quickly if it stays within the stretched horizon, because if you stray within the stretched horizon, it takes m squared time to travel from this point to this point. So outside the stretched horizon, the only thing available to carry information is the Hawking radiation. So we're going to assume that the Hawking radiation carries the black hole information and scrambles it. And let's look at the photon sphere more carefully. And what we're going to do is we're going to divide it into cells. And what we require is that the time it takes to cross the cell, from outside to inside and back, is the same as the time it takes to cross the cell radially and back. And this is order m when viewed by an outside observer. So each of these cells is filled with Hawking radiation, as seen by an outside observer, which is actually, we will use the amount of Hawking radiation as seen by an observer hovering in the cell, which means that the temperature of this Hawking radiation when you're close to the horizon is incredibly high. Okay, there's a constant times the surface area of the event horizon number of cells altogether, and the vast majority are right outside the event horizon. And within the constant factor, this is the amount of information contained by the black hole. And details of the subdivision, well, the cells are, so I've drawn this picture using Schwarzschild coordinates, and that means that there is length contraction in these coordinates when you're close to the horizon. So these cells, as viewed from someone hovering in them, are really have a constant aspect ratio. It's just the Schwarzschild coordinates that make them look very skinny and long near the event horizon. Okay. So as seen from an outside observer's viewpoint, the Hawking radiation has the same frequency everywhere. And the redshift makes it much greater frequency, appear to have much greater frequency to an observer hovering over the horizon, which is because the time is dilated for this observer, just from general relativity. And we design these cells so the round trip from one side of the cell to the other takes time m, and they're all of the same size as the dominant radiation wavelength in the Hawking radiation seen by an observer hovering inside the cell. And what this means is that each of them contains a constant number of bits of information, if you use the formula for how much information does thermal radiation contain. Okay, so what are the requirements for strong scrambling? To scramble the information, we take the northern hemisphere and the southern hemisphere of a black hole and have this be relatively untangled with the southern hemisphere. And we want to end up with a generic pure state, which means there's nearly maximal entanglement between the top half and the bottom half. So that means we need to carry order of A information from the top half to the bottom half. Now, how can we carry it in this cell structure? Well, we could stay near the surface of the black hole. But if we do that, the number of cells that it has to pass through is order of m, and the time it takes to pass through a single cell is order of m, meaning that we need order of m squared time, as viewed from an outside observer, to carry information along this path. Now there's another path. We could have a path that starts on the inside, goes onto the outside, and comes back and lands back in the horizon over here. And there are lots of geodesics that do this. And, well, there are only a constant number of, so this path actually crosses log m cells, which means it could traverse it in log m time. But there's only a constant number of cells on the outside boundary of the photon sphere, which means if we only have one unit of information, one bit going through a cell at each time step, then to get order m squared information from here to here, we need to take order of m time, order of m squared time. We need to move cell order of m squared qubits through the cell, which means we need m cubed time total, because it takes m time to move a qubit through the cell. And there's only one qubit in this cell at a time from Hawking radiation. Now what we can do is we can divide the photon sphere of the black hole in two sections by the plane, and we want to say that order of m information goes from the bottom half of this diagram to the top half. And if you look at how how many cells separate the bottom half from the top half. There are order m cells, and you get order a, which is order of m squared, information from one side to the other. We need time order of m squared. So there's order of m cells here. We want to get m squared bits from the top half to the bottom half, which means we need to take order m time, or order m steps. Each step takes order m time, and that means that the total time is order of m squared. So you cannot do scrambling, you cannot do strong scrambling in time less than m squared if you want to satisfy all of our assumptions. So, okay. So this is the argument that strong scrambling time or entanglement scrambling time for black holes has to be order at least m squared. Now I want to end this talk with a whole bunch of speculations. One thing that a lot of people have thought about and come up with many, many different proposals for is what are the microstates of the black hole which contribute to the entropy? Because if the entropy is order of the area, there must be a whole bunch of microstates which give you the entropy. So what could they be? Well, if you look at the Hawking radiation around the black hole, assuming that the Hawking, or viewing the Hawking radiation from a stationary observer, it has order of A entropy. So maybe the Hawking radiation is the microstate of a black hole, which gives it the entropy. Now, one thing you could object is that the Hawking radiation is mostly virtual. So in some sense, it doesn't really exist. But I mean, just because it's virtual, does that mean that it cannot have entropy? I don't think so. I think it could have entropy. So I think this may be the solution for where does the entropy of a black hole come from. It comes from its Hawking radiation, or its unruh radiation in the black hole. Okay. And next question is, how can information come out of black holes? So we've been assuming that the information you throw into a black hole comes out of the black hole. Well, one possibility, which I certainly don't know enough physics to know whether it's reasonable or not, is there are quantum fluctuations in the horizon. As the horizon is, if the horizon is fluctuating in height by quantum fluctuations, this might let information that fell into black holes long ago come out, because suddenly the horizon is fluctuated so that the information is outside the horizon. So in order for causality to be preserved, this information would have to come out at essentially the same point that it went in, but there's really nothing, there really doesn't seem to be any arguments for why this couldn't be the case. So maybe this is how information comes out of black holes. And with my arguments, I think there are several things that could happen. Maybe the strong scrambling time is really order of m squared. So all these people who have been assuming somehow that the weak scrambling time and the strong scrambling time are equal are wrong. Maybe unitarity breaks down for black holes when the information actually doesn't come out, which I think is a possibility that you have to consider. And maybe there's some really new and completely radical physics operating near the horizon. So, given the choice between these three possibilities, I would really think that the obvious choice for which one is mistaken is this first one. Okay, let's see. I'm essentially out of time, I believe, and this is the end of my talk. So thank you.
I have a question. What does virtual mean?
I don't think there is such a thing as virtual particles.
Okay.
Okay, so there are real particles which last for a long time. There are virtual particles which are just edges in Feynman diagrams, which means if you believe a Feynman diagram is something real, these virtual particles last for, you know, I want to say incredibly small fractions of a second, but there is nothing wrong with drawing a Feynman diagram where you have a particle that lasts for, 0.1 second. And so there's a continuum between real particles and virtual particles, which means that saying virtual particles cannot carry information, but real particles can carry information is complete nonsense, in my opinion.
Okay, let's thank Peter again.